My name is Jessica Beckmeier. I am doing my capstone project on internet scams. Title is Internet Scams: What They Are, Their Effects, and How to Avoid them. So this presentation and my project and paper is split into 3 parts. So our first part is going to be just general information about internet scams. And first I'm going to talk about the common types of internet scams. So first up are phishing attempts. Those are your emails that you get, and RIT sometimes will send out messages about them saying, hey, don't open a link in this email because it's fake. These are the random emails you get, a random text, random phone calls, pretending to be, sometimes it'll be the IRS, sometimes it'll be like your utilities company, sometimes it'll be RIT. They're basically attempts to get information. Whether that information is like your bank account information so that they can go into your bank account and take your money, or if it's your identity information so they can steal your identity. Another category of scams are the advance fee scams. That's where they claim you've won a prize and you have to pay them a fee to get it. Fake prizes is kind of in that same category. The Nigerian prince scam was a big one a few years ago. Somebody would email you claiming to be a Nigerian prince who wanted to move large sums of money into the US, and you had to pay him a couple $100 to move the money, and then you would get your payoff. Of course, there was no payoff, and they were just stealing your money. Another category is romance scams or the imposter scams. The romance scams prey on those who are trying to find love online. Basically, the scammer pretends to be a love interest and will say things like I'm in jail, I need you to pay my bail, or I'm having a medical emergency and I need you to send me money for this. Imposter scams are basically the same thing, except the scammer is pretending to be like a grandchild or a nephew or something like that. And the last category I have listed here is the tech support scam. These can come either in the form of like a random phone call with somebody on the other end. Usually it's just a text-to-speech voice saying that we've detected that your computer has an issue, call this number back. And another way that these scammers reach victims is through websites that just throw up fake pop-ups that say that they look scary and they say your computer is infected, call this number. So the victim will call the number, the scammer gains access to the computer via remote access software and makes it look like the computer is infected, and then demands payment for an expensive solution, which often is not anything. So next I'm going to talk about who is at most risk for internet scams. So when most people think of people getting duped online, usually the first thing you think is old people, because old people didn't grow up with this technology like us younger generations did. And old people see things and often are quick to believe them. So the research I did, most of this information comes from the Consumer Sentinel Network Data Book from 2018, which is it's a set of data published by the Federal Trade Commission about complaints that they received for online fraud. And it's categorized 2 different categories of identity theft and fraud. So you can see the graph there. The two groups that are most likely to report being being victims of fraud are the 50 to 59 and 60 to 69, which are old people, boomers. And one thing that surprised me was that I thought that people that were 19 and under, like kids who don't know how to be safe online, would be the victims of a lot of scams, but it turns out that they are actually the group that gets scammed the least. So the next thing I'm going to talk about is why people fall for these things. There are three broad categories of factors. There's the message factors, which this is basically how real the scam message looks, how good a job that the scammer did to make the phishing email or the fake virus pop-up look legitimate and real. So these are things like using the actual name of an organization, using the logo of the organization, like actually using, say this, it's a phishing email trying to imitate the IRS and saying, oh, you owe taxes. They would actually use the IRS's logo and try and make the message seem as official as possible. Experiential factors are, these have to do, the other two categories of factors have to do with the actual victim. Experiential factors are like, sorry. Experiential factors are exactly what they seem. It's basically somebody's experience online. Things like computer literacy, knowledge of scams, how well somebody can sniff out a scam, how likely they are to be able to tell that it's a scam and not a real message. Dispositional factors are a little bit deeper. These have to do with the victim's personality. These are things like how well they're able to control their impulses, if they're isolated, their psychological well-being, and how likely they are to trust other people. For example, somebody who's really quick to trust random people that they don't know are a lot more likely to fall victim to a scam than, say, somebody who's in general pretty distrustful and takes everything they see with a grain of salt. So the next section of my presentation is the impact of being scammed. First, I'm going to talk about the emotional impact. There hasn't really been a lot of research on the emotional impact, not nearly as much as there has been on the financial impact of being scammed. But clearly, from the research that I've done, being scammed does have a significant emotional impact on the victim. One thing that may be surprising is that sorry, so you just give me like a second. Okay. One thing that may be surprising is that the emotional effects that people that are victims of scams feel are often similar to the effects of being the victim of violent crimes. These feelings include things like being depressed, feelings of anxiety, being embarrassed or ashamed, harboring feelings of anger and resentment towards the scammer, and some people even have have feelings extreme enough to lead to suicidal ideation. Another issue with victims of scams is secondary victimization. This is basically victim blaming. A lot of people may be afraid to report the scam or tell their loved ones that they have been scammed in fear of being called stupid or naive. Because if, for example, if an old person gets scammed online and they lose their whole savings and they have to go to their kids and say, hey, can I borrow some money? I got scammed. And they may be afraid that their kids would say, oh, wow, you're so stupid. How could you fall for that? It's because you're old, right? But a lot of people do not report the fact that they've been scammed because of the fear of secondary victimization. The emotional impact of a scam is also heavily correlated with the financial impact of the scam. One paper that I read in the course of my research graphed out a quantified representation of the emotional and financial impact of various different kinds of scams. And the two lines that were graphed out, one representing financial impact and the other representing emotional, were nearly identical in shape. So, financial impact. The financial impact has been studied a lot more than the emotional impact of scams. This data I also got from the FTC data book. Oops. So, in the US, the amount lost due to internet fraud in 2018 was nearly $1.5 billion. In the UK, the losses were reported to be about £2.3 billion in 2019. In this graph, you can see the amounts reported to have been lost laid out. As you can see, mostly it's small amounts of money ranging from $1 to $1,000. One thing that I thought was interesting is that there's this huge amount of people that lost $1 to $1,000, and it drops off sharply in the next dollar amount bracket drops off more, and then drops off even more sharply in the $3,001 to $4,000, and then it rises again sharply in the more than $10,000 category. And obviously, it makes sense that the higher the financial impact of the scam, the higher the emotional impact of the scam will be. Because most people don't have just $1,000 laying around that they can afford to lose. So the last section is, how can we fix this problem? And obviously, it's a big problem online. It's not just online, but it's also robocalls, random text message, and I believe strongly that the solution to this problem will come through education. The FTC has several web pages dedicated to this education. This slide has just the 5 tips that they have on their how to avoid being scammed website, and it's pretty much common sense. but not everybody knows this. So people have to be told. And it's good that the FTC has this website, but for people like old people that don't know really a lot about computers, they may not be able to access this website because maybe they don't know how to do a simple Google search. So an issue with reaching out to people is just, how do you reach out to the people that don't know how to use the internet? According to a study done by the AARP, about 70% of older Americans have a smartphone and 62% have a computer. Only 72% of people over the age of 55 are considered digitally literate. The study that I got this from defined digitally literate as being able to pass a basic test on computer functions, such as using the mouse, opening and closing files, and judging the accuracy of the information presented, which is a big part of being able to avoid scams. In comparison to younger people, 84% of young people younger than 55 were digitally literate compared to the 72% of people older than 55. So the question is, how do we effectively reach these people that may not know how to access the FTC website or online news articles? We have to go old school with newspapers, television, radios, magazines. A lot of old people do still read printed newspapers and still read printed magazines. New subscribers over 50 are a lot more likely to read printed news than they are to read news online. A lot of people over 65 get the AARP magazine monthly. A lot of times, oops. That was a mistake. Okay. A lot of times the AARP magazine will run articles about trending scams and what you can do to protect yourself. News stations, television news stations and radio news stations can also occasionally run informative articles to inform people that are still watching the news and people that are still listening to the news on the radio. And when anybody else, or when all else fails, younger family members can spread the information to their loved ones via word of mouth. And that's the end of my presentation.
Thanks, Jess. Nice job. Oddly enough, in the 6 semesters I've been doing this course, there's only ever been one other person who's talked about phishing, and that person presented this morning. so we've had you're the second one today to talk about phishing. So, you know, of those 5 tips that you put up there from the FTC, the one that I think applies not only to this sort of thing, but applies in general is do not act immediately. I think that's a great advice. You know, oftentimes when you're writing an email, for example, you get an email and you want to respond, it's usually not, especially if there's some emotional aspect to it, it's usually not a good idea to respond. So it applies here too, because, you know, oftentimes it's a good idea to think first, right? So if you immediately respond, you're in much greater danger then. So I think that's a fairly simple message. And
yeah, and that was one of the dispositional factors for why people may fall for these scams, is that people that don't have as much impulse control are
right.
ability to respond to the messages immediately and lose money.
Exactly. So they need to be threatened. Okay, so my main question is, what about the other side of this, the scammers? What you've talked about are the scams. But the scammers, I'm interested in, do you know anything about, in your research, did you come across any statistics on prosecution and punishments for this?
Not like in the course of my formal research that I did, but like I like to watch videos on YouTube about people like baiting scammers. One guy that I watched like breaks into the scammers' computers and finds out where they are, and a lot of them are in India. And then he reports them to the India cyber police, and often nothing is done about it.
So they're not in Nigeria? I always thought they were in Nigeria.
No. So it's illegal in India, but people do it and the police don't enforce it. I don't know if it's an issue of not caring or not having the resources to do something about it.
Yeah. Yeah, okay, so really nice presentation. I think it's something that, you say the solution is education, and, we're in the education business at RIT, and only a few people get to go to college compared to the general population. So I guess that's all we've got, but I don't think it's going to resolve the problem. It's probably going to get worse. I spent some time in China, and in China, even though they have a lot of censorship, and so a lot of stuff is not reported online, but a lot more stuff in China happens online than in the US. For example, payments. I mean, it's almost impossible to use money, cash in China. You've got to go through some sort of payment process, electronic payment, in order to get anything. Mm-hmm. So I would, the more electronic we become, more dependently electronically we become, the more opportunity to get scammed, I guess. So the prognosis is not really great. Anyway, I really enjoyed your presentation. And Meg?
Thank you. Just great job. I really like how methodically you laid out, what the issue is, what causes it, what contributes to it. I'll say in watching this, I'm reminded so clearly of, and Stephen, you'll remember me sharing this with you, 3 years ago when my dad unfortunately got scammed. And, I think it was all three of the factors that you mentioned. So, the way the email looked so legitimate, it was quickly followed up by a phone call that had a caller ID number that matched what it said on the email. He was just 6 months out from an Alzheimer's diagnosis, so he was a vulnerable person. And his, I would say his experiences as an 84-year-old really did not involve very much in the way of education about this. And I'll say the ramifications of it, and that's really what I appreciated in this, was that you really focused on the emotional impact and the emotional fallout. Because this was really damaging to my dad in terms of his confidence, and it actually was like the tipping point of a lot of different things that then happened afterwards. But I think framing it in terms of the not just the financial impact, but the emotional impact it will have on individuals, I think is really important. He has 3 daughters in the area, and so we both really, or all 3 of us really pushed him to file a police report. But he was so ashamed that he was able to be scammed, even though the police officer handled it so well, because he was like, I can't believe how legitimate this is. But it didn't matter. It was like the damage was already done. So I
think it's important to focus on the emotional impact. I mean, financial impact is also important, but at the end of the day, like, you can make that money back. I mean, I guess that's just my perspective, that I say that coming from a middle class family that's not really experienced like extreme poverty.
Sure.
But the financial impact does tie back into the emotional impact. Like, obviously, if you're right on the poverty line and you get scammed out of $100, that was probably like your car payment. And now, oh, you can't make your car payment, or oh, you can't make rent, or oh, you can't eat. And obviously, it's going to be a lot more emotionally impactful, no matter the amount. It's going to be more emotionally impactful, like the less extra money you have just laying around. Like, if you're a billionaire and you get scammed out of $100, it's like a drop in the bucket.
Right. Well, and I also thought, you know, I'm curious about your thoughts on actually that chart and why there was such a drastic dip. And I wonder, you know, from the 1 to 1,000 all the way up. And I wonder how many people just choose not to report it because it is, it's just validating that they were fooled, they were duped. So I think
there is a breakdown of amount by age group in the FTC data book, but I'm not sure. But I think there may be a breakdown in it.
Yeah. I do wonder how many people just choose not to report it because they're embarrassed.
Mm-hmm. And often there's not really a lot that the police can do. They can't do anything.
Right.
They don't.
Right.
They don't, like, Rochester Police Department doesn't have any jurisdiction in India to do anything to the scammers. Mostly what they recommend that people do is go to their bank and tell the bank, because it's the bank that would be able to do something about it.
Right. Well, I thought that was great. Really nice job.
Thank you.
Okay, so now, Paul, it's your turn. Take it away.
All right. You guys hear me all right?
Yep.
All right, perfect. Let's see here. Let me just do a test click. All right, we're good. All right, so I am ready whenever you guys are.
Go ahead.
Is there any way I can, let's do that. All right, so my name is Paul Jepsen. My presentation is called A Look into Constants. It is about the origin story and upbringing of the famous constants pi, the imaginary unit, gravity, and the speed of light. So the first thing I'll talk about, some opening thoughts, such as the inspiration and why I chose to do this. We're kind of introduced into constants at a pretty young age. It might be like 7th or 8th grade when, you know, your math teacher says, all right, well, the area of a circle is pi r squared, and pi has the value 3.14159. You can just use the button on your calculator to do it. And that's about it, really. I mean, we're young at the time. We don't really have to think too much into it. That's it. A couple years later, you might take a physics class. You learn that, you know, gravity has the value 9.81 meters a second squared. The teacher might give you a few equations to use it. He only really cares that, you know, you use the equation right, you get the right answer at the end. There's not much thought process into where that number comes from. And take it for granted because, like, gravity is something that affects us every second of every day of our lives. So this project was to figure out, like, the whys and the hows of some of the constants that we've used thousands of times through our educational career. And the first thing we're going to do is talk about the difference between a physical constant and a mathematical one. So a mathematical constant has a fixed numerical value and does not directly involve a physical measurement. So essentially, once you find the value of pi, it stays that way forever. Pi will never change. A physical constant is universal in nature and is fixed with time. Physical constants are generally discovered through measurements. So we can measure gravity, and maybe tomorrow a big physics breakthrough occurs and it changes our understanding of how the world works. So those numbers can be changed as a result of something like that. So we'll start with the mathematical constants. And the first one we're going to talk about is pi. This is probably the one that most people in their lives are introduced to first in their life. Pi has a value of 3.141592653 ... It goes on infinitely. It is an irrational number, meaning that there are infinite digits and there's no discernible pattern as to the digits. You cannot guess the next number based on the previous ones. The simplest definition of what pi is the ratio of a circle's circumference to its diameter. So, earliest known discovery. The ancient Egyptian and Babylonian societies had a number representing what pi was over 4,000 years ago. They didn't name it pi, but that's essentially what it was. They essentially took a piece of rope, made it into a circle, took another piece of rope, measured the diameter, and then compared the two pieces of rope. And as a result, they got numbers that varied from exactly 3 up to 3.2. You know, they got the general ballpark, but wasn't super precise. All right, so who had a more precise discovery of pi? That would be this guy here. That is Archimedes of Syracuse. He did so around 250 BCE. He calculated pi as between the values 223 divided by 71, or 3.14085, and 22 over 7, or 3.14286. Both of these numbers are within 0.05% of pi's definitive value, so he did very good for over 2,000 years ago. It's pretty impressive. And I'll explain how he did it. How did he do it? He used a method called perimeter circumscription, in this case for a circle. And his closest approximation came from a 96-sided equilateral polygon. So essentially what you do is you circumscribe a polygon of some number of sides within a circle, then you add up the sides of the perimeter, and since it's equilateral, all you have to do is measure one length and multiply it by the number of sides, and you divide that by the length between opposite points, and there's your guess of pi. Now, he did it for a 96-sided equilateral polygon, and as you can notice, as you increase the number of sides of the circumscribed polygon, it becomes hard to tell it's not even a circle. Like, I can't even tell the difference at 24 sides that this is not a circle when it's not, let alone 96. And he did it by hand, so it's kind of amazing. It's very fascinating. But yes, he multiplied one of these little lengths by 96 and divided it by the diameter, and that's where he got his value for pi. All right, next we'll talk about the imaginary unit, I. I has the value of the square root of -1. The imaginary unit, and subsequently imaginary numbers, were introduced by mathematician Raphael Bombelli in 1572. That's this dude here. He created the rule set for how the multiplication of I works. And you might remember this from like later years in high school. You have, I to the first, second, third, fourth power, and then it just tends to repeat. He made this because you can't take the square root of a negative number. You can take the square root of a positive number, and it comes out to be positive, but you can't multiply two negative numbers and get a negative number. That's why you can't take the square root of a negative number. So the imaginary unit I kind of is a way to bypass that problem, and he wanted to do that. So some more history. The inception of the imaginary unit was met with great backlash. Many mathematicians thought the imaginary numbers had no practical use and learning the technique was pointless. So much so that the word imaginary was deemed fitting and acted as a derogatory term towards the research, like the use is imaginary, so it's a fitting name. This couldn't be further from the truth because in my experience, I went to RIT initially as an engineer, specifically electrical engineering. I've dealt with so much it's ridiculous. I've used pi thousands of times. I've used imaginary units thousands of more times. There's so many practical uses for it. Back then, they just didn't know. They had to learn. And that's thanks to these guys. A little quick there. Imaginary number is not fully accepted as a useful mathematical concept until Leonard Euler. It looks like it's pronounced Euler, but it's actually pronounced Euler. And Carl Friedrich Gauss added their own contributions. So that's this guy. This is Gauss on the top. That's Euler down low. Euler proved that e to the I pi plus 1 equals 0, which shows that an imaginary number could be related to real numbers through sines and cosines. E is another constant, one I'm not going to be really talking about, but if you can convert this into sines and cosines, and by doing that, you can prove that something imaginary somehow equals real numbers that we know. So this is a huge proof right here. And then Gauss showed that complex numbers can use their own coordinate plane and subsequently went on to create several mathematical proofs off that work. And a lot of those proofs, like I said, is stuff you'll get into in like electrical engineering. A lot of stuff is related to Gauss. All right, so that Now we're on to the physical constants we're going to be talking about. And we're going to start with gravity. You might be wondering, all right, why is there two G's? Why is there a big one and a little one? Well, they represent different things, but they're related. Little g represents the gravitational pull that Earth exerts on us. Its value is 9.81 meters a second squared. It's the reason we're on the floor right now and not arbitrarily flying through space. Gravity is holding us down. Big G represents the force of attraction that any two objects have on each other. So anything, including us in this Zoom meeting, we might be very far apart right now, but there is a very tiny force of attraction between us, or anything in the room you're sitting in right now. There's something pulling you towards it. The problem is those numbers are so infinitesimally small that it doesn't affect your daily life compared to that of like regular gravity, Earth's gravitational pull. So you don't experience it really. And it's shown by how tiny the constant is. Big G is equal to 6.674 times 10 to the negative 11 meters cubed divided by a kilogram times second squared. The units get kind of confusing. It's essentially space divided by the weight and then two factors of time. It's a little wacky. All right, big G is responsible for the value that little g has. And you can see that in this equation here, where little g is equal to big G times the mass of something divided by the radius of that something squared. So if we plug in the mass of Earth, which is 5.972 times 10 to the 24 kilograms into m, and the approximate radius of Earth, and remember, Earth does not have a constant radius, so we're just going to assume the average radius of 6,370 kilometers. You plug both these numbers in, and then the value for big G, and sure enough, you will find that little g is equal to 9.81 meters a second squared. And going off that, since Earth is not perfectly round, the radius changes. As such, the value of gravity is different at different points in the world. And here are the two most extreme cases. The lowest gravity you'll experience is in Mount Nevado Huascarán in Peru at 9.7639 meters a second squared. And the highest value is at the surface of the Arctic Ocean at 9.8337 meters a second squared. Both those numbers are relatively close to the average gravity, but if you were to fall, say, 10 feet at both locations, there would be a few milliseconds of difference of time it takes you to reach the floor. All right, so who discovered gravity? That's this guy. That would be Sir Isaac Newton. He was the first man to conceptualize the existence of gravity. It is said he came up with the idea when he witnessed an apple fall from a tree in 1687. He concluded that the only way an object would enter free fall from rest would be if some unknown force was acting upon it. An apple can't just arbitrarily decide, all right, I'm going to fall now. Something has to be pulling it down. As the apple grows in size, its weight becomes heavier, the gravitational pull on it becomes heavier, and the tree can no longer sustain that, and it falls. He also postulated this force, which he was the one to name it gravity, was the reason the moon never flies out of its orbit into deep space. Without gravity, we wouldn't have a solar system. The planets wouldn't rotate around each other, around the sun. The moon wouldn't rotate around the Earth. We wouldn't exist, essentially. Gravity is very important. All right, so we've learned all this stuff about gravity, but where did this value of big G come from? That would be this guy. His name is Henry Cavendish. He performed an experiment in 1797 that resulted in the first numerical value for big G. He calculated big G as 6.74 times 10 to the negative 11 meters cubed divided by kilograms times second squared, which is only 0.99% off of today's value. And that's over 200 years ago, using this rudimentary device. It's called a torsion balance mechanism. Explaining it in great detail would be very time consuming, but I'll give you guys a quick rundown. Essentially, the user, you guys can see my mouse, right?
Right.
Okay, so somebody will pull this string and that will rotate this around, which rotates these giant metal spheres. And once those start rotating, they actually have an attractive pull on these little tiny spheres here on the left and right side. And the more they get attracted, the more this little string here starts to spin and wind. And what you do is you measure the amount of spin in this little twine per unit length, and that represents this number that he found. Now, I have asterisks here because it's worth noting. Back then, they didn't distinguish mass and weight, which are different things. So this number is not exactly what he calculated, but if you would convert the number he got to today's standard units, this is what it would be. And again, he's only less than 1% off. And as such, after this, many more experiments occurred. And this is the second most measured constant in history, big G. And that's behind only the last one we're going to be talking about, the speed of light. The speed of light is 299,792,458 meters a second in a vacuum. Now, if you don't know what a vacuum is, it's essentially empty space. It's so empty that there are 0 atoms within it. It's not realistic. You can't really have a true vacuum, but that would be the speed of light if a vacuum did exist. As such, the speed of light has different values depending on the type of medium it passes through. We witness it all the time going through air. Air is something that's all around us and it's what we see light through. So the speed of light traveling through air is valued at 0.9997 C, or 299,702,547 meters a second. It is 89,911 meters a second slower, which is a huge speed in its own right, but literally nothing in comparison to the speed of light's top speed. So it only drops a minor amount. And at this point, you might be wondering, all right, why is the letter C representative of the speed of light? Like, why the letter C? Well, this guy's responsible for that. His name is Wilhelm Weber. In 1856, he was the first person to denote the speed of light as C as an abbreviation of the Latin word celeritas, which means speed, fitting. The not often English word celerity, which means the speed of wave propagation in fluid, stems from this Latin word. And as a final note, Einstein decided to start using the letter C to represent the speed of light in 1907. He initially used capital V, but once he swapped to the letter C, it became canon at that point. Once Einstein did it, people were like, all right, we're gonna do that. Letter C it is. All right, the speed of light was viewed as instantaneous until several physicists began to question that notion. The first one would be Galileo. He was the first one. Galileo Galilei. I actually didn't know his last name was Galilei. That was fascinating to me. In the early 1600s. And how he did it is depicted in this animation right here. He essentially had 2 people stand about a mile apart with lanterns that had shutters on them. And one guy would open the shutter, revealing the light to the other guy. And when the other guy saw the light, he would open his shutter back. So the light would kind of ping pong back and forth, and they would try to measure a lag in time between the two. So he concluded that light was, quote, extraordinarily rapid, and at least 10 times the speed of sound. Now, for reference, the speed of sound is 343 meters a second. You multiply that by 10, 3,430 meters a second is nowhere near the speed of light. So he tried. You have to couple that with the fact that the human eye takes roughly 0.2 seconds to process information, and then the result is an experiment that didn't exactly go as planned or didn't get a very accurate number. But he got a number at least. So who was the first guy to get a respectable velocity for the speed of light? That would be this guy here. His name is Ole Romer. In 1676, he calculated the speed of light based on how long it took Jupiter's moon Io to reflect the light back to Earth based on where Earth was in its orbit around the sun. So if you look at this diagram here, Earth in its rotation around the sun is much closer to Jupiter and Jupiter's moon here than it is here. So as such, the light will travel faster to Earth, and over here has a much longer distance. He calculated the time difference it took light to hit Earth as 17 minutes between these two sides, left and right. And as such, he was able to calculate a speed for the speed of light. He got 214 million meters a second. Now that's 28.62% off roughly of today's accepted value, but that's still, like, he got the number of digits right and he got an insanely high speed. So it's a very respectable guess or experiment result. And as such, like, starting from that point, the speed of light went through so many different experiments that used completely different methodology from this one. And there's tons of different times measured. That's why it's the most measured constant in history. And its current value was actually discovered as recent as 1983. So not even that long ago, we were finding the speed of light. And with that, there's not much left to say. That's pretty much all the information I have. So I had to say thank you. Hope you guys enjoyed.
Sure did. Meg, do you want to go first, or is it me? I can never keep track.
Sure, I'm happy to go first.
Okay.
So Paul, I found that so fascinating. I guess I'm curious, in terms of the constants,
Mhm.
are there a finite number of constants? I mean, it's a mathematical term.
I mean, there's a lot of constants out there that all have different purposes. Like, I could just start listing them and I probably wouldn't even do it justice, but yeah, there's definitely probably, like, in terms of physical constant, there would be a finite amount at some point. Like, constants represent something, right? There can only be so much representation of things on the earth, but I don't know the number offhand. There's a
Right.
lot.
Okay. Okay. And I guess my next question is, so what do you want to do with this? What's next?
I'm glad you asked that, because I initially had that in my final slide, but I had to, like, cut stuff off just to shave it down a little bit. But essentially, like, what I could do is I could write a book off of it technically, and have, like, it'd be more encompassing. There'd be many more constants, and it'd probably be aimed at younger college students that could probably find the information useful. That, and, like, I could make an argument for a school to offer a class that talks about the history of constants. I think that'd be worth listening to. You could maybe do one class encompassing all, or you could have two that have, like, or two split. One would be mathematical constants specifically, and the other one would be physical constants.
I think that the history that you added added a lot of context to the constants.
Mhm.
So I think that would be especially interesting
Yeah.
in thinking about how they all came about. Just the idea of pi and all the mathematical pieces. You know, I can hear the crunching happening in my brain. But I do think, I think you made it really interesting. So thank you. I enjoyed that.
Thank you.
Hi, Paul. So there is no such book? This book?
I mean, I imagine a book exists, but, like, I didn't necessarily find one in my research. And I imagine some universities out there probably have a class that encompasses those topics, but again, I don't think RIT does. So
I think I thought it, you know, your distinction, maybe it's a commonplace, but I wouldn't have thought of it and wasn't aware of it. The distinction between a mathematical concept and I guess a physical or natural constant. So it sounded like we are more sure of gravity, the constant value for gravity, than we are for light. Is that true? Because you said that the measurement of light changes.
I'm not entirely sure, because you can make a whole bunch of measurements and experiments to find the speed of light, and maybe the end result is you find a 1 meter a second difference. That's kind of what was happening. Whereas something like the gravitational attraction between two things, that's kind of a little more, I don't know, in depth, I feel. So it might be the case where the speed of light was figured out more, but the other one is just more difficult in nature to figure out.
So I like the idea that we don't know everything, so these things can change. Whereas
Yeah.
if it's not related to what we know, if it's independent of that, then it can be, quote, constant. But
Yeah.
so you've got the measurer, and you've got the measurement, and then you've got the reality of the thing, right? So
Yeah.
so those are the three variables, and one assumes that the reality of the thing really is constant, but
Yeah.
the other two variables can be less constant. So it's a fascinating field. So light travels through space. Did Einstein's depiction or understanding of space as curved, how does that relate to the passage of light, to the speed of light?
Well, I mean, light tends to bend around extremely large objects. So that was probably tied into old Romer's experiment of measuring the speed of light bouncing off of the Jupiter's moon and back to Earth. You can see light before the sun's actually there. It goes around.
Yeah.
If there was an eclipse, for instance, it would bend around the moon or whatever.
Right. So you're going to be are you going to become a teacher? Is that what
No, I don't plan on becoming a teacher.
So what are you going to do when you graduate?
I don't exactly know yet. I'm just trying to get there.
Are you going to graduate at the end of this
Yeah.
semester?
Yeah.
So you are almost there.
Yes. I'm trying to get there.
So I'm trying to think of a cute way of putting your own personal trajectory from graduation and then beyond into terms of your presentation, but my brain isn't working, so I'm gonna let that go. Does anybody else have any questions? Jess, do you have any questions? Nope. Okay. All right. Well, I enjoyed both of your presentations very much. It's my job now to remind you, you have 2 papers due in the next couple of weeks, and I know Meg and I will be looking forward to seeing them. Of course, presenting is quite different from actually writing, completely different format. But anyway, we will look forward to receiving your papers, and then you'll be done. So congratulations, and thanks a lot.
Yeah, congratulations to both of you. Great presentations. You're so close to the finish line. So stay healthy in the next couple of crunch weeks, and best of luck to you.
Thank you.
See you later. So you switched the recording up this time?
Thank you. I need to